Let's now try our first actual application of Faraday's law. And this application is also going to serve for us to give you an illustration where we are very careful with how the signs work out. It will give us a good illustration also of Lenz's law, not in the motional context, but in the Faraday law's context. So here's the basic idea of the particular device that's going to make up our example. So I'm going to make a circuit. And this circuit is going to consist of, once again, our favorite resistive load that we're going to end up driving a current through. And now I'm going to wire this through one of these, my favorite coils, right? There's going to be some kind of a solenoid device. So it comes down and it loops around. We've drawn these before. There's a little gap where we can't see as the wire goes down behind. And so I'm going to have a circuit completed with a device like that. And now I'm going to specify my solenoid here, the relevant parameters for this solenoid, or that it has cross-sectional area A, and there are capital N turns or loops making up my solenoid. And the way this circuit operates is there's going to be a changing magnetic flux. I'm going to have a magnetic field here that is going to ultimately be changing. And this magnetic field happens to have, in this case, an upward direction as it goes through the loops in that wire. So this is my magnetic field B, and I'd like to point out that this B is going to be changing here as a function of time t. So the question then is going to be, well, and there could be a magnetic field in other in other regions, not just inside of this solenoid, but for now we'll just label the magnetic field when it's inside the solenoid as some value B. Very good. Now, the way this device operates is that the changes in this magnetic field clearly are going to induce changes in the magnetic flux through the various turns of this coil, which therefore should generate an induced EMF via Faraday's law, and that induced EMF therefore will tend to drive a current which will flow through this resistor. So we're going to just make a guess right now, and we'll think about it and confirm things later. We're just going to guess that the current is going to be flowing upwards through this resistor. My guess may turn out to be wrong. If it happens to be wrong, well, we know then we will just find, but if we keep all of our signs straight, if it happens to be wrong, that's not necessarily a huge deal. It just means the value of the current that will come out of our calculation will just be a negative value for that current. Okay, so if we want to solve this system to determine the flow through the current, we may not know exactly here where to start, but we've done so many circuits before. We know we want to do Kirchhoff's law or something like Kirchhoff's law. So I'm going to basically circulate around my circuit through a loop. So I'm going to go in a loop here all the way around my circuit. And I'm going to be very careful, though. I'm not going to say that the sum of the voltages is 0, because now we know Faraday's law tells us something slightly different. So I'm just going to write down Faraday's law very carefully. Faraday's law states something like the sum of the voltages. It says that, well, when I integrate minus E dot dl around my closed loop, and that, of course, is the sum of the voltages, each voltage is minus integral dl, and adding them up all the way around the loop is minus E dot dl. But now we know instead of getting 0 when we do that, what we end up with is the time derivative of the magnetic flux through our particular pathway. Now, the way I want to carry this through then is I'm going to say, all right, let's start at some location, and I'm going to integrate E dot dl around a path, and the path I'm going to choose is going to go through my resistor, and then I'm going to stick inside my conductor here, where I know the electric field has to always be 0. So when I do that, of course, the first thing I experience is going through my resistor, which is going to give me a plus or minus IR. But for this sense of direction that I've defined for my current, this is the upstream side of my resistor. This is the downstream side for that sense of current flow. So as I go through the resistor, the choice I have to make is negative. After that, notice I'm inside a perfect conductor. I'm inside a stationary perfect conductor. So therefore, I know the electric field is everywhere 0 inside the rest of that conductor. So there are no other terms for integral E dot dl because I'm imagining the rest of the system that isn't the resistor is a perfect conductor. So that's interesting. So I just have that one term for integral E dot dl, but now I have to take the time derivative of the magnetic flux, and I have to be careful about that magnetic flux. So this is the magnetic flux that goes through my path. Notice how my path consists of n turns, right? There are n actual loops in here, each with area A. So there's going to be a flux associated with each one of those. The flux I haven't figured out yet, I want to be careful with my signs, has to be plus or minus the value of the magnetic field times the area A is the flux. But I have n turns, so I'm going to get n contributions, one from each turn, and each contribution is integral of B dot dA. And it's that integral of B dot dA that we next have to try to evaluate very carefully. In fact, let me erase these signs because there is no sign that should appear here yet. Those signs come in when we do B dot dA. Now, let's think about this. To do B dot dA, I need to know what is dA. dA is the normal to my area vector, but that area vector is defined, right, by right-hand rule number 2. If we think about how I go around these loops, right, the current comes down this loop here and around, right? So it's coming down, it comes across in front, back to the left and back. So if I focus just on this one loop, you can see, using right-hand rule number 2, curling my fingers around in that kind of clockwise, counterclockwise looking direction, right? You see the fingers should be curling across in front, and then to the right in front and to the left and back. When I do that, I see that the normal vector to this surface area is actually straight up. So let me try to draw here a normal vector. It's gotten quite a bit messy here, but the normal vector is pointing upwards. So the normal vector, which defines the direction of the area vector, is upwards. That means then that when I go to evaluate this integral, let me rewrite it here a little bit. I have the time derivative of n times, then I've got the surface integral of breaking out the dot product, magnitude of b, magnitude of dA, times the cosine of theta, but b is imagined to be straight up inside my loop. And the normal vector we decided from right-hand rule 2 was also in the upward direction. So they are both in the same direction. So I have the cosine of 0. And we know the cosine of 0 is 1. So I'm getting a plus sign on this side of the equation. Let's see here. N, the number of loops, is a constant. It doesn't depend on time t, so I can pull that out of the derivative. The magnitude of b, I can't pull that out of the derivative because it's changing in time, but it also doesn't depend on location in space. I imagined a constant field in here, so I can at least pull b out of the integral. What I'm left with is just the integral of dA, which then just gives me the total cross-sectional area of each of these loops, because I've multiplied by the number of those loops. So what I end up with then is n times d by dt of b has been pulled out of the integral of t, just the magnitude of b, times then a. Or I can write my whole equation here in shorthand, minus I times r, that was my left-hand side, equals then, factoring out my constants, na times dB dt, so that then finally I can solve for the current. The current flowing in this situation, I, is equal to, I just have to divide both sides by minus R. It's going to be minus NA dB dt divided by the resistance R. So that's how I would solve for the current in a circuit like this that involves a changing magnetic flux. The second thing I'd like to check now is we notice the sense of direction of I had guessed wrong. This evidently is the wrong direction for the current to be flowing because I came out here with a negative sign. The actual current must flow in the opposite direction. Well, let's see. Let's see if Lenz's law works. Let's see if this is clearly the wrong direction for the current I. Now, if the current I were flowing in this direction, we should think about what that current would do to the magnetic flux. Now, we see here in this equation that an increasing magnetic flux should lead to a negative current. We're going to see here now if we have a positive current, what would happen to an increasing magnetic flux. So if I had a positive current like this flowing down through my coils in this direction, once again, the right-hand rule would tell you when you think about the flow, when you think about your fluid model, if we take, for instance, this piece of the wire that's coming horizontally across in front with a current flowing off to the right, and you do your right-hand rule for that, you'll notice that the circulation is going to be upwards on the inside of the solenoid. So a positive current I, in fact, is going to generate an upward magnetic flux inside. And that would be a problem, because by Lenz's law, if I have an increasing magnetic field inside, the induced current has to be in a direction that tends to decrease the flux, not further increase it. The only way to make a magnetic field from my current that is in the other direction to tend to fight that increase in the magnetic field would be to run the current in the opposite direction, and so it's perfectly consistent with Lenz's law, and we could have used Lenz's law to guess this sign that we get the minus sign out here. So I'll put a little Lenz's law label there with, again, the happy professor, because the no free lunch principle of physics seems to have worked out quite well in this case as well.